Everyone, can you hear me? Can you hear me? Yep. I think I'm audible. Today we'll be solving two problems again, and today's problem will be like one of the problems will be pretty important, like it's a difficult problem, which is median of two sorted arrays, and this is like one of the most asked questions in your interviews. And the second problem that we'll solve today is and in fact, this is the first problem we'll solve is the kth largest element in a stream. Now, this is a very easy problem. This is like if you know the trick, it's a pretty easy problem. But again, like it is also a pretty popular question with respect to interviews. In fact, I myself have faced this question a couple of times in my interviews, right? So this is a very popular question with respect to interviews, but it's a fairly very simple problem if you understand the logic. And the second problem, which is median of two sorted arrays, it's a complicated problem. I'll definitely say it's a complicated problem because yeah, definitely would get the logic, but writing the code would be a bit challenging as well. We'll discuss both of these problems, and these are very important. Again, like as I said, these are very important when it comes to interview point of view. So let's actually start with the first problem, that is kth largest element in a stream. The problem statement is you are given an input stream ARR of n integers. You have to find the kth element of each element in the stream, and if the kth element doesn't exist, you have to return -1, right? So what it tells is the elements are coming to you one by one. Like first one is coming to you, then two is coming to you, then three is coming to you, then four is coming to you, like that. When each element comes in, you have to tell what is the kth smallest element, kth largest element, and if kth largest element is not there, you have to report -1, right? So you have to report -1. So that is basically the question. So for example, in the first case, we can see k is 4 and n is 6. So we have 1 2 3 4 5 6. So when one comes in, what is the kth element? Only one element is available, one. So there is no k is 4 here, fourth element is not there. After that, 2 comes in. How many elements are there? There are two elements, right? 1 and 2. So what is the fourth element? Fourth element is not there. Then 3, 1 2 3. What is the fourth largest element? Still there are three elements, fourth element is not there. Then 4 comes in. So what we have right now is 1 2 3 4. So what is the fourth largest element? The fourth largest element will be 1, right? So 4 3 2 1, this is the order, and the fourth largest will be 1. Now 5 comes in. What is the fourth largest element? What are the elements that we have? 1 2 3 4 5. What is the fourth largest element? It will be 2, right? So 2 will be the answer. Then 6 comes in, and that time 3 will be the answer, right? So this is the question. So every time like each element comes in, you have to report what is the kth largest element after that element comes in. So that is the question. So let's actually see how we can solve this, right? So let's actually take a good example. Maybe we'll take it here. Okay. Now, how do we solve this, right? To solve this, what we have to do is there are multiple ways, right? There are definitely multiple ways to solve this, but we'll directly jump into the optimal way. So let's say we have some data structure, right? So we have some data structure. What does this data structure contain? It will contain the k maximum elements, right? K maximum elements that we have found till now, right? K maximum elements that we have found till now. Now there are two operations that are happening, right? First is report the kth maximum, and second is insert an element. Now let's talk about both of these operations one by one and what this data structure should support. First is report the kth maximum. So we have, what does this data structure? This is a data structure. What does this data structure contain? It contains the k maximum elements that we have found till now. So the top k elements, like let's say 5 4 3 2 1. So these are the top 5 elements. Let's say k is 4. So we'll contain the top 4 elements, 5 4 3 2. So this is the top 4 elements that we have in the data structure. Out of them we want the, and what do we want? We want the kth maximum element. We want the kth maximum. So what will be the kth maximum element? This data structure contains the k maximum elements. So out of this k maximum element, we want the minimum element. So this report kth 1, that is report kth, will be the mean element of data structure, right? Mean element of data structure. Why? Again, this will contain the k maximum elements. Now we want the kth element, kth maximum element. So that will mean the minimum element in this data structure. So the first operation is basically we have to find the minimum element of the data structure. The second operation is insert an element. Now two conditions can happen. First is the new inserted element v is greater than the mean element and v is less than the mean element, less than equal to the mean element. So v is greater than the mean element and v is less than equal to the mean element. In the second case, when v is less than equal to the newly inserted element is less than equal to the minimum element, does it fall under the category of the k maximum elements that we have found till now? No, right? So it doesn't fall in the category, so this will never be a part of this data structure. So in this case we do nothing. This will not be a part of the data structure. In the first case, v is greater than the minimum element. So that means v definitely is a part of the k maximum elements, because the minimum element in this data structure, which contains k maximum elements that has been found till now, v is greater than the minimum element. So definitely we should replace the minimum element. So in that case, what we should do is we should remove the minimum element, and add v to the data structure. So these are the two operations. These are the two operations that we want to support, right? And that will solve the problem. So we want to do both the operations optimally. Is there a data structure that can do both of these operations optimally? There is. Which one? Priority queue or a heap, right? So priority queue or a heap will basically do both of these operations, right? So what we'll do is we'll maintain a min heap, because we want the minimum element. So we'll maintain a min heap, and whenever we want the kth element, we'll get the minimum element from a heap. So get minimum element, and whenever we are inserting an element, and if v is greater than the minimum element, in that case remove minimum element, that is the top element of the heap, and insert v. So each of these operations will be order of log n time complexity. So these all will be also log n, removing and inserting, removing the top element and inserting into it. So both of them will be log n. So the total complexity will be n log n, right? So there are n operations, and every time you are doing, so there are n times we have to do these operations. So the total complexity becomes n log n. Just to dry run on some sample case, let's say we have something like this, that is 2 1 5 6 2 3 4 5 and k equals to 3, right? K equals to 3. In this case, first we have this prior heap. So first 2 is coming in. So the size of it is definitely less than k, so we'll just insert. So 2 is inserted. After that 1 comes in, 1 is inserted. After that 5 comes in, 5 is inserted, right? Now we have 3 elements. So for the first 2 elements, kth element will be -1. Now we have 3 elements. So what we want the third smallest element, which is 1, right? The minimum element of the queue. So the answer will be 1 here. Now 6 is coming in. So 6 is greater than the minimum element 1. So definitely 1 should not be here, and 6 should be replacing 1. So it will be 6 5 2, right? 6 5 2, and the kth minimum element will be the smallest element, that is 2. After that 2 comes in. Now 2 is less than equal to the smallest element, so it will not replace. So the kth element remains 2. 3 is greater than 2, so 3 will be replacing 2 definitely, and 3 will be coming in, right? So 3, and the kth minimum element will be 3. Then 4 will be replacing 3, so 4 will be replacing 3. So write 4 here, and the kth minimum element will be 4. Then 5 is coming in. So 5 is definitely greater than the minimum element 4, so 5 will be inserted. 5 will be inserted, and the third minimum element will be 5. Then 2 is coming in, it will not be inserted, so 5 will be the kth minimum element. So this will be the answer, right? Pretty simple. Now once you like, basically it's about using a heap, right? If you understand why we should use a heap, you will be able to solve the problem pretty fast. So let's write the code for this. Priority queue int vector int, we are creating a min heap, and greater int pq. So for int and vector int answer, vector int answer. So for int I equals to 0, I less than n, I plus plus, if uh, what will be the condition here? If first is if the size is less than k, right? Pq dot size is less than k. In that case we should just add, right? Pq dot uh, push arrk, and else what we should do? Else we should see int min element equals to pq dot top, uh, q dot top, I think it was it top? Let me just check. Plus plus priority queue methods, let's just check. So it's push and pop, push and pop, and top, push pop top. Okay, so push pop top, so we want dot top, and yes, min element is pq dot top, and min element min element is less than the current element that we are inserting, so that is arri. If, sorry, it will be pushing arri, not k. If it is less than arr of I, in that case we have to remove it. So pq dot pop and pq dot push arr of I, and so that should be it. And finally here we'll check if pq dot size is equal to k. In that case, right, answer dot pushback pq dot top, else answer dot pushback -1, and finally we'll return answer, right? So this is the solution. Let me know if you have any doubts on this. You're getting the output correct? Okay, so this should work ideally. Okay, this is working. All right, so pretty simple problem. I hope that there is no doubts here. Like, it's pretty simple. Once you get the logic that you need to use a priority queue, it should be straightforward, right? And this is again, like, this is a very common question. So if it's asked to you in interviews, like what is the kth largest element, like you have to dynamically answer that, or for every sub array you have to tell that, or something like that, then you can definitely use priority queue, right, or a heap. So that's the first one. The second one is a good question, which is we have to find, it's a hard question, it's definitely a hard question. So we have to find the median of two sorted arrays, right? And they can be of different sizes, and that's fine. Like, we can make a general solution for this. So we are given two sorted arrays. So there are two sorted arrays that's given to us, and we have to find the median of these two sorted arrays, right? We have to find the median of these two sorted arrays. So for example, what is median again? The median is when you have a sorted array, when you have a set of elements in a sorted fashion, the middle element will be the median, right? So that's basically the definition of median. So here we have 1592367. So if we combine them together into a single sorted array, 1 2 3 5 6 7 9, what is the middle element? The middle element is 5. So median of this two sorted arrays is 5 and the answer should be 5. Right. So similarly in this case we have even number of elements 4, 6 and 1, 2, 3, 5. So what is the if these two are combined into a single array, what will be the values? 1, 2, 3, 4, 5, 6. Right. So what are the two middle elements? 3 and 4, I think, or 2 and 3. It should be 3 and 4. Yes, 3 and 4, and then 3 and 4 plus by 2, that is the average of the two middle elements, that is 3.5 should be the median. Right. So you are given this task, you have to find the median of two sorted arrays. 159, 2. Let's write it down. Right. 159, 2, 3, 6, 7. Okay. The brute force way, I'm not explaining the brute force way a lot, but I think it's pretty clear to everyone already. What you can do is you can merge these two sorted arrays, right? You have two sorted arrays and you want one sorted array out of them. You want one sorted array out of them, or two sorted arrays, you can merge them. You can use the merge operation to merge them, and the time complexity for this will be order of n plus m, where n and m are the sizes of the first and the second arrays respectively. Now this is a brute force solution and will not use this. So this is one way we can definitely do, but we can do it better in a better time complexity. So let's understand that. Okay, so first of all, let's write this in the form of a sorted array, right? So it will be 1, 2, 3, 5, 6, 7, 9. I think that should be 1, 2, 3, 5, 6, 7, 9. Right. So let's say, so basically we can divide it into two halves. That is, this one is the median, right? So we basically divide it into two halves. Both the halves will be equal in case of even arrays, and in case of odd sized, or like the sum is odd, in that case the left half will have one more element. So we can divide it into two halves, and the last element of the first half is the median. So if we look into this carefully, 1 and 5 are coming from the first array, and 2 and 3 are coming from the second array. Here 9 is coming from the first array, and 6 and 7 are coming from the second array. So this is how the entire structure looks. 1, 5 is coming from the first array, 2, 3 is coming from the second array. Similarly here 9 is coming from the first array on the right hand side, 6, 7 are coming from the second array, right? 6, 7 are coming from the second array. So that's basically like how it is partitioned, right? Now one thing to note here, so what we'll do is, what we want to find is, if we want to find the median, right? If we just find this 5, right? If we just find this partition point for the first array, right? We can definitely tell where the median is. How? Because in case of median, in case of odd array or even array as well, the sizes of the two halves will be same or will be differing by 1 in case of odd and even, right? So if in this case it is odd, right? So we know the left size, that is the left half size will be what? It will be 4, 7, 8 by 2, that is 4. The left size will be 4. So we know that we need 4 elements, right? Now if we are telling that we are taking 2 elements from the first array, so definitely we will be taking 2 more elements from the second array, 2 and 3, and thus 1 element from the first array will go to the right hand side, and 2 elements from the second array will be going to the right hand side. So if we just able to find this partition point, we can find the median, right? Now what is the condition for this to be a valid partition? Let's understand that, right? So if you see, 5 is definitely less than 9, because 5, this is the sorted array, right? And 9 is coming from the same array as 5. So 5 is definitely less than 9. But we cannot ensure that 5 is less than 6. But for this to be a median, this to be a valid partition, 5 should be less than 6. So the first condition is 5 should be less than 6. The second condition will be 3 should be less than 9. 3 should be less than 6. It is definitely true, because 2 and 3 and 6 are coming from the same array and it is sorted. So 3 is definitely less than 6. But 3 should be also less than 9. So that is the second condition that we want to ensure, right? So more formally, if we, let's call this one to be L1. Let's call this one to be L2. this one to be R1, this one to be R2, right? So more formally we are just saying that this basically means that L1 should be less than R2. Similarly, this says that L2 should be less than R1, right? Less than equal to, basically less than equal to, right? So it should be less than equal to R2, this should be less than equal to R1. So that should be the condition. In that case, this is a valid partition. And what we said is, if we are just able to find the partition, partition 5, we can tell that we can find that the other values, right? We can find 3, 9, 6, everything, like using this concept that both of the halves will contain same elements, or one element more will be contained in the left half because of odd size, right? So that's how we can easily find. Now coming to this, let's actually do one thing. Let's actually try to formulate all possible valid partitions. So this is the valid partition, right? But let's formulate all possible partitions and see like how we are getting the valid, or how many valid partitions are existing. So first is, we will not take anything from the first array, and the second array will take, we have to take 4 elements, so we'll take 2, 3, 6, 7 from the second array. On the right hand side, from the first array we'll have 1, 5, 9, and from the second array we'll have nothing. So that's one way to partition, right? That's one way to partition. The second way to partition will be, we'll take one element from the first array, that is 1. The second array, from the second array we'll need 3 more elements, because we need 4 elements. So 2, 3, 6 will be coming from the second array. Here 5, 9 will go, and here 7 will go. So that is the second. Third way to partition is, we'll take 2 elements, 1, 5, and here from second array we'll take 2 elements again, 2, 3, because we want to size of 4. So we have taken 2 elements, right? So third element will go to the second part, so 9, and here 6, 7 will go. And another way will be, we'll take 1, 5, 9, we'll take all the 3 elements, and here we'll take just one element, that is 2. For the right hand part there will be no element, and for this one it will be 3, 6, 7, right? So these are the ways to partition. These are the partitions that are there. Now let's see, for the first case, it is definitely not a valid partition. Why? Because 6, here we have 6, here we have 5, so this is violating this condition, right? L2 is less than equal to R1. This condition is violated. What does this mean? Let's understand this properly. What does this mean? This means that we have taken more number of elements in the second part. So we should get rid of some elements from the second part and take more elements on the left hand side from the first part. So that is the answer, the answer, or the partition, where the partition should lie, should be on the right hand side. For the first case, it is telling the where the partition should lie should be on the for this one, it is saying the partition should lie on the right hand side. For this as well, see, 7 is less than 1. That means we have taken less number of, 7 is less than 1, so that means we should definitely push 7 and a few more elements on the right, and 1 should come on the left. So that means the answer should be, or the partition wherever it has been made, should be on the right hand side of the first array. Coming to this is a valid one, so this is valid. Coming to the last one, see, again this is invalid. Why? Because 2, okay, whenever something is missing, right, whenever something is missing, here we will do is, on the left we'll take int minimum, that is minus infinity, let's call it minus infinity. On the right we'll take plus infinity, right? So here it will be plus infinity. So 2 and infinity definitely won't compare, but 9 and 3, this is violating the condition that L1 should be less than equal to R2. This condition is getting violated, right? So this condition is getting violated means we have taken more elements from the first array. We have taken more elements from the first array. So we should get rid of some elements from the first array towards the right and take some elements from the second array to the left. That means the partition, wherever we have done the partition, it should move to the left hand side. Because we have done the partition here, but we should move to on the left hand side, because this is not a valid place to make the partition. So basically, so we see that there is a monotonic approach, like For some cases we are moving the partition on the right hand side, like for lower values of the partition. For higher values of the partition we are moving it to the left hand side. So we can use a binary search approach, right? We can use a binary search approach. So again, the condition of the conditions will be, first is if L2 less than equal to, if L2 greater than R1. If L2 greater than R1, that means we have taken more elements. Like wherever, let's say this is the first array, this is where we have done the partition, this is the partition point, right? So wherever we have done this, we are taking more elements from the second part. We should take less elements from the second array. That means we should move our partition on the right hand side. So in this case it means that our partition should be moving to the right hand side. So that means low equals to mid plus 1. That is, our search space should be on the right hand side. The valid partition position should be on the right hand side. So we are discarding this first half entirely. This can't be a valid place to place the partition, right? Similarly, when L1 is less than R2, in this, sorry, L1 is greater than R2, sorry, my bad, not less than, greater than. If it is greater than R2, that means we have placed some partition, right? And the number of elements we have taken here, that is L1, it is not L1, actually the last element is L1. L1 should definitely go on the right hand side. It should not be on the left hand side. That is, our partition should be moving on the left hand side. In this case, we should do high equals to mid minus 1. That is, the valid position for the partition is definitely on the left hand side. So we discard this entire region, right? We discard this entire region, entire right hand side. So this is how we do binary search. This is the condition for doing binary search. And yeah, this is the condition for doing binary search, right? So this is how we'll do binary search, and we'll find the answer to be answer, right? We'll find the answer that is the perfect place for placing the partition, right? And once we get the partition, right, once we get the partition, so what do we have here? We have this one to be L1. In the second array, this is L2. Here we have R1, and here we have R2. How do we find the median? Now in case it is odd number of elements, so in that case it will be the maximum of L1 comma L2. Why? Because this is forming the entire left part, and whichever is the maximum will come to the end. So we want, and this will contain the median because it is odd size, the array is odd sized. So the maximum of L1 comma L2 will be the answer. If it is even size, so this is for odd. If the summation of the two array sizes is even, in that case it will be whatever is the maximum here, so max of L1 comma L2 plus the minimum of R1 comma R2 and divided by 2. So that should be the median, right? Because again, like this one will be the minimum, that is, let's say R1 is starting this, so these are the two middle elements, so it will be L1 plus R1 by 2, right? Okay, so this is basically the logic. Let me know if you have any doubts, but we can go to the code directly. Writing the code is a bit challenging, so let's try to understand and write it properly, right? And try to name the variables as well properly. So let's call n to be the size of the first array, right? So array1 dot size. Let's call m to be the size of the second array, so that will be array2 dot size. So what is the number of elements in the first half? So number of elements in first half will be what? Number of elements in the first half will be what? It will be n plus m plus 1 by 2, because we'll take one, like in case of even it will be n plus m by 2 basically, and in case of odd it will be like one more, so that's why n plus m plus 1 by 2. That will be the number of elements in the first half, right? So we'll start with the binary search. So for the binary search we need low will be 0, high will be equals to n, right? Low equals to 0, high equals to n. So what does this, what are we binary searching on? We are binary searching on how many elements do we want to take from the first array on the left part. how many elements from the first array we want to take on the left half, right? So while low less than equal to high, int mid equals to low plus high by 2. Low plus high by 2. Now what is this low plus high by 2? What is this? This is the number of elements. So this is the number of elements in the number of elements or cut point for first. So, or let's call it num elements in left for first. Number of elements in left for first array is mid. So what is the number of elements in left for second? What is the number of elements on the left hand side for the second array? What is the total number of elements on the left hand side? Number of, this will be, so number of elements in first half minus number of elements in left for first, that should be the number, right? So we are taking 0 to mid minus 1. So these many mid number of elements will be on the first half, right? So that is basically yep. So basically 0 will be mid, sorry. So 0 to num elements in on left side of first, left side for first will be minus 1 will be the elements in the first half. Similarly, this minus 1, 0 to this minus 1 will be the elements in this first half for the second array, right? So let's define the L1 R1s now. L1 equals to what? It will be, we'll check if number of elements in left for first is equals to 0. If it is equals to 0, in that case it will be int minimum, otherwise it will be array 1 of this minus 1. Number of elements on in the left for first minus 1. Similarly, int L2 equals to, we'll check if this value, number of elements in left for the second, is equals to 0. If it is equals to 0, it will be int min, otherwise it will be array 2 of this minus 1. Similarly, int R1 equals to, we'll check if this value is equals to the end of the array, that is all the elements are on the left half, right? All the elements on the left half, in that case this will be int max, otherwise it will be array 1 of this, right? Int R2 equals to, we'll check if this value num elements in left for second is equals to the end of the second array m. In that case it will be int max, otherwise array 2 of this value. So we have this, right? Now if now what is the condition? First is if L2 is greater than R1. If L2 is greater than R1, this means what? We have taken more elements from L2, so we should definitely try to take more elements on the left hand side for the first array. So our pointer should move on the our answer will definitely be on the right hand side. So low equals to mid plus 1. Else if L1 greater than R2, that means we have taken more elements, so our pointer will definitely be on the left hand side. So in that case high equals to mid minus 1. Else, right? So if it's n plus m by 2 is if it's even or odd, we will check here n plus m modulo 2 is equals to 0. If it is even, in that case we'll return maximum of will return what? Will return the max of L1 L2 plus min of R1 R2 divided by 2.0. Else will return the max of L1 comma L2, right? And so that should be the binary search, and finally will return 0 on 0, like if it's it should never come, right? Now we are assuming here that we are assuming here that we can go up to both the ends, right? We can take 0 elements or we can take n elements as well. So definitely we can do this. So we'll always try to make the first array, like the array on which we are binary searching, should be lesser one, right? Because we can then go to both the ends. So if n is greater than m, in that case we should just return the median. That is, the first array is greater in size, so we should just return the median of arrays of array 2 comma array 1. That is, we are just uh, like reversing the array, right? We are just like doing with array 2 should come first, then array 1. Like our first array should definitely be of smaller size, right? So that's basically the question, the code. Let's try to run this. So this is working. Let's try to submit. Okay, so this is working fine. Let me know if you have any doubts, and this is how you can solve this problem. This is a very important question when it comes to interviews, and it is like asked a couple of times. So definitely like understand how to solve this, and so that you can solve it in the interviews, right? So let me know if you have any doubts on this. I believe it's clear. Like what we are doing is we are trying to binary search on the perfect place to make the partition in the first array, and if we are able to do that, we can definitely, like if we are partitioning the first array, we can easily find what will be the elements that are coming from the second array on the left hand side, and those things, right? Yes, everything should be available. Everything should be available on the channel. So let me know if you have any doubts on this. I think it should be clear. You can find it in the playlist, Karan. You can find it in the playlist. Okay, I believe there are no doubts. In that case, yep, I'll thank you guys for joining, and I'll be seeing you on the next class. So this is, I think this is the last part one. So the next class will be our last class. So yep, I'll be seeing you there with some more good questions. Thank you.